Ladies and gentlemen, my name's Tom Graham, and this is my co-founder of MapD, Todd Mostek. We're here to talk to you today about the power of real-time and interactive big data analytics, particularly powered by our GPU in-memory database. So what is MapD? We built a super fast GPU database into the memory on the GPU cards. At the moment, we're using the K40 Tesla cards. What does it do? It's the world's fastest real-time big data analytics platform, particularly focused on interactive visualization. And we made this great demonstration using Twitter data. Even though our platform, MapD, as an SQL database, can take any kind of data, we're going to show you our demonstration of 1 billion tweets using Nvidia's GPUs, and it can scan the entire database and return results and visualizations in just milliseconds. So first, because we're live streaming tweets onto our database, if you have your mobile phones out and you have a Twitter account, please turn on your location services, switch it on. It's the little arrow that looks like that when you pull out the tweet. Take a photograph, do something like that, and it will send GPS latitude and longitude data through Twitter's API. We'll pick that up in MapD, and it should pop up on the screen just in while we're talking and giving the presentation. So we'll have a look and see what's been going on a little bit later. If you want to tweet out any of the hashtags, we've got MapD, SC13, Nvidia, SC13. So what is MapD's core innovation? So we took the full memory bandwidth and the parallelism on GPUs and from scratch coded a database, an SQL database, into that environment. So it runs about 70 to 1,000 times faster than other in-memory database solutions for for big data analytics. Because of all of that memory bandwidth on the GPUs, all of the threads, and all of the visualization power that you have coming out of GPUs. And we can use any kind of data because we're an SQL database. So let's flip over to our demonstration and give you a little taste of what it looks like. We're going to talk about Haiyan, the superstorm that flew through the Philippines most recently and unfortunately. We've got 1 billion tweets on 8 Nvidia Tesla K40s. That's about 23,000 cores, 2.3 terabytes per second of memory bandwidth. All of that data is stored in memory on 96 gigabytes of GPU memory and about 30 teraflops of compute power. And the important thing to realize here is that nothing is pre-computed. Every single search, every time we move the map, every visualization, the database will scan the entire set of data, billions of rows in our column store database, and return results in real time. We're also streaming live tweets, so you can stream data onto the system. And the result is interactive and real-time analytics. So let's go over to the presentation. So here what you're looking at is the world in tweets. That's about 120 million tweets for November. And the red dots are live tweets streaming in. So let's add a map. There we go. Let's go to the analysis plane. Open that up. And let's zoom in to the Philippines.
Just big, yeah.
We'll take off live tweeting. So here we are. Now let's search for Haiyan up in this little search box. We're searching tweet text here. And we're returning all the tweets that mention the word Haiyan. You can see Japanese weather data services tweet the eyes of storms, so you can see the path that Haiyan took. We can put this on a heat map, which measures tweet density. And we can also animate that. So we can look at the storm developing and moving over time. So you can see it start off there, moving across, and over the Philippines, the density of tweets really increases, and you can see that indicated by the red on the heat map. So let's stop that. Yolanda was the name that the storm was given in the Philippines, and so we can search for particular tweets as the storm was arriving. This kind of thing is particularly useful for emergency services support, locating disasters, and it turns out that people tend to tweet when they're in trouble. If we click on a tweet, we can see something in talking about the barometer of our wind chime. We can click on that. It's an Instagram picture, and you can see some images of when the storm hit. So we'll flip back over. So my co-founder Todd is going to talk to you a little bit more about the technical aspects of MapD.
Great. Hi, everyone.
Yeah, so come over to the computer.
So yeah, I've been building MapD for the last, I would say, year and a half. It came partly out of I don't have a conventional computer science background. I was a Middle Eastern Studies master's student, but got into computational social science, took a database course at MIT. I was at Harvard at the time, and started building. One of the problems I had is I was trying to analyze tweets from Egypt. There was, say, maybe just 50 or 100 million tweets, but to geolocate those, basically join them on the fly with Egyptian census districts to do demographic analysis. Some of the things we'll show you that we can do with MapD. To do that, it would take minutes to hours using Python or C, and it just wasn't acceptable if I wanted to explore the data. So I was like, what if we could do this in milliseconds? And so that was kind of the impetus to start developing this. So like Tom said, it's a full SQL database. You can do query on the back end without all of these nice visual basically all these nice visuals. It's just select whatever. You can basically, again, search any size data set if you can scale up to multiple GPUs and multiple nodes in milliseconds. The nice thing, you have GPUs, so you can actually do the visualizations on the fly. So these maps are all rendered on the GPUs and pushed to the front end, to the web browser. We're also looking at doing 3D graphics with basically universe data sets, like data sets of galaxies and stars and other data. Like I said, any type of data that's relational, any data set, and we now have live streaming of the data onto the system. So it's basically an analytic workload database, but you can do normal updates and inserts. And as you can see, we're streaming hundreds of tweets on a second, and you tweet and bam, you can see yourself on the map. And it's not being pushed to the front end, it's actually being pushed to the back end, and you're running a regular query to pull that into the front end. The nice thing, until we've had Nvidia's largesse and these beautiful K40s, we were running on regular gamers GPUs, like 680s, 780s, and Titans. You get really great performance per watt and performance per dollar performance from these cards. And we can support with by using batched queries, where even though the memory bandwidth is really, really high on the GPUs, you can still hit memory bandwidth by using memory bandwidth limitations, by putting multiple queries on the same scan of the data and caching the predicates for those scans on the basically shared memory of the GPU. We can actually scan a billion tweets basically for 30 users times 30 frames a second. That's in progress, but it will be up shortly. We're optimized for GPUs, particularly CUDA. I mean, that's what I started this all on. But we're looking to expand it into x86, Phi, AMD, and maybe even potentially mobile processors. Sorry, AMD, OpenCL. The interesting thing is that it doesn't have to be just running on GPUs. The next version of this is basically a hybrid execution engine that will basically partition the data as needed, move it into separate buffer pools on GPU and CPU memory, and so it can scale to any size data beyond what can fit on GPUs. And those can be executed concurrently on CPU and GPU. So right now, just talking a bit about our Tweetmap, there's approximately 500 million tweets a day. You may know this, 400 to 500 million tweets a day on Twitter. Of these, just because they're really interesting from a visual and analytic perspective, we've been using just the geocoded tweets, which are 7 to 10 million, about 2% of these tweets, which means that you're sending them usually from your mobile phone with your GPS enabled. You have to put the little arrow on. And this is as precise as the GPS is on your computer. Like outdoors, probably 20 feet or less. Indoors, the accuracy may vary, but still probably within 50 feet. We're not just keeping the text of the GPU. We keep all the metadata on the GPU as well. Coordinates, the timestamp, user, follower graph, reply information, hashtags, whether it comes from an Android or iPhone. We can show you us mapping that as well. So one of these things is you might see a lot of tweet maps out there, but generally what these tweet maps are doing is they're basically pre-canning the data. Either they're computing tiled maps based like by pre-histogramming the data out, say overnight or over even a few days, and then showing you that. Or they're just giving you like the real-time tweets, just the tweets coming in on the fly, sending them to your browser. I think the ability to query like a billion item data set over the web and having multiple people do this on a public demo, I think it's fairly unprecedented. So MapD is hopefully this new tool to interactively visualize data. So here's just it's a bit excessive, but we're turning on all the layers just to show you like what MapD can do. This is love, querying love. So what you can do is you can search tweet text in that corner. You can search by user, so you can find all users' tweets. The live stream is coming out on the left if you're on the current time frame, if this time window is butted up against the right. Here's a word cloud, but you can do bar graphs, scatter plots against census data. We'll show you some of that. You can animate over time, as you already saw. You can identify trends and even compare different terms against each other. And, of course, you get the heat map, which you saw. Choropleth is basically breaking down by like countries, states, counties, census blocks. And we can do that really, really fast. We can do these spatial joins on the fly, which is great. And so you can do this demographic analysis of, people who like this brand, what's their average income, things like this. And change the base maps. And also, we're really into this social sharing. So you can like find something that's interesting to you, because we believe that people can collaborate and say, oh, this is an interesting phenomenon, like say social science researchers. You can share it and send it out as a link in an email or a tweet. Okay. So basically, we can both correlate with external data sets. One thing we're working on is not just having Twitter, but say having Twitter data, weather data, cell phone density, brand preferences, accident data, crime data, and being able to join all that on the fly.
Okay, so I think we'll go and show some of the demos.
Yeah. Are we running out of time?
No. That's where we're up to. So let's switch over to the map.
Sure.
Okay, great. Okay, so let's zoom in on America. And let's put on a heat map. Let's turn off the points. And let's say there ain't no place like home. Let's look for usage of a word ain't. And you can see that it's pretty much a southern thing. Let's try hella. It's kind of a western thing.
So this is the percentage of tweets. It's not just the raw numbers. It's actually the percentage of tweets by area.
We're based in Cambridge, where we say wicked. And you can see that it's pretty much a New England kind of thing.
How about Dunkin' Donuts versus Starbucks?
Dunkin' Donuts, very much just located in the northeast. So let's do something like snow, and then we can animate these heat maps. So let's click snow. Let's make the data range something like that. And let's click animate. And you can see these storms rolling across, and we're obviously coming up to a snowstorm here. You can see it hit and reach mentions of snow all the way down to South Carolina, so it must have been pretty bad. It was on Wednesday last week. So let's extend the time graph out again. Let's have a look at some more of a census kind of data. So we're going to turn off the heat map, turn on chloropleths. You can see it by country, by state, and by county. There are 4,400 counties in the US, but we're going to go back to state. And down in the analysis plane, if we go to chart, scatter plot, we do it by county, and let's do it by percentage. And now it's analyzing snow, but let's do something that we... Can you guys... this is going to... Yeah. So down here, you might just not be able to see that. Let me exit out of this. We see that?
You guys
no,
see that
still
down
not.
there at the bottom?
1 second.
I think it's fine.
Yeah.
You're going to have to... Okay.
That's okay. So down here you can see it's currently correlated with population, but we can change that to per capita income. So we're looking at mentions of snow, but let's change that to something more interesting like Whole Foods. And what we're looking at here is percentage of tweets that mention Whole Foods. Each one of these dots is a county, and you can see this regression line indicates that as people's income increases, they tweet about Whole Foods more. Let's try.
Behind that is actually a full query on the back end where first you aggregate. You have to join each tweet to the county, and then you do a group by county. So it's quite involved query to actually just build that one graph. Over a billion tweets or something.
Let's try something like Walmart. And you can see that income increases, people tweet less about Walmart. You can then break that down to counties and see exactly where people are tweeting about Walmart as opposed to other areas. Let's go back to state. Apple, A-P-P-L-E, is an interesting one. So let's look at that over a different census variable. Population of your county under the age of 18. So as the percentage of people, we're up on counts, let's change this to percents. Put it on a state level. Nope.
Uh-oh. That's what I was telling you
county.
about. Small bug.
Have we lost it?
Well, it's just the front end. We need to refresh.
Okay. You find that you can see that as for Facebook and Apple, as people get younger, they talk less and less about that. So moving along, you can see live streaming of data here. So Todd, would you like to come over and talk more about the technical aspects?
Sure, thanks. Cool.
There you go.
Thanks. So one way to think about computing or doing a database across multiple GPUs is it's very similar to a distributed database, except that you don't have some of these worries about consistency. So basically, we have this shared nothing architecture where data can be partitioned between any number of GPUs and then eventually any number of nodes. So in this system that we've been demoing on, we have 8 K40s, but I often demo right off my laptop with one small GPU for a smaller data set. So it's pretty flexible. So you can imagine data, like I said. This is node 1 or computer 1, node 2. They all have their disks, and they all have any number of devices. So basically, across each GPU and each node, similar kind of to MapReduce, you're running this filter, like where does text contain rain? You find the matching tweets, and then you basically histogram that out or group that by like X and Y pixel, but you're binning by X and Y pixel, or for the time graph, you're binning by time. So it's expressible as an SQL query, actually. And then you have to merge these basically into one on either the master node or on one GPU and move it to the host to push across the internet one final heat map or histogram.
We're running out of time,
Okay.
so let's move right along.
Yeah, I think I can
skip through that part.
if anyone wants to talk about it, we can do that later.
Mm-hmm. You can see how they build the maps in the database backend. So what makes really effective big data tools? We came to this problem as social scientists, and we were looking at small systems running on local hardware that anyone could access, so it was really about the democratization of big data analytics. It was about interaction with live data streams, so you could take a little idea, iterate upon it, play with the data, build a hypothesis piece by piece, and look for the big idea. Or maybe you'll find a dozen other big ideas just like it. It's about the socialization of data-driven insight. So taking that share this map function, sending it to your friends, asking them what's interesting in the data visualization that you're looking at, and getting some feedback. We're open source. The kernel of our database architecture will be made open source in the next couple of months. So we're a startup. We're hoping to offer supported enterprise-grade database in the cloud or as an appliance. We do platform integration, tailored database and analytics solutions, and we also build free public demonstrations powered by MapD, like the Twitter map that we've been looking at. So please have a play with our live demo. You can find it here. It's open to the public. And let's see if we can go to the demo right now and find tweets in Denver. Right down to the convention center. Hopefully they've been live streaming in. Just wait 1 second. So let's do Colorado. R-A-D.
Denver Convention Center or Colorado? Oh yeah.
Denver Convention Center?
I guess they both work.
So we're pulling these maps from OpenLayers and Google, which takes a little bit of time assembling that on our front end. You can see that here is the convention center and all the tweets when they load up. We can color by user. So you can see these ones down here. Let's see. Here is a tweet that I just did before. Here's Todd presenting. So there he is. Some of you in the crowd. What else did people through? Map graph. SC13. Here's another one. I think this is. I did this while Todd was talking just before. It's loading up the Twitter. It should. Oh no, that's a. Oh, there you are. That's our crowd. So you can see that you can do interactive, real-time data analytics.
Here, let me see if mine will pop up. Ready?
Did it send?
It's putting pressure.
It's a lot of pressure.
Think so. Okay.
No, maybe live streaming is not on. Okay, let's move along. Nope. So special thanks for Nvidia for hosting us and supplying us with hardware. It's been great to work with them. MIT CSAIL and Professor Sam Madden. So, any questions?
First, thank you for this wonderful software. My question is, does this SQL support join and subqueries, correlated subqueries? Secondly, that if we cost per effective, we can use K20 instead of K40. It has only 6 GB. And if you do grow by, you need some buffers. So effectively, you can hold only 4 GB or less data. So this is really extremely limited by the memory of the GPU. So what's your perspective on that? What's the data size you can handle?
So yes, sorry, your first question again was, sorry, remind me of your first question, sir? Before I get to the second.
Can you run on cheaper hardware?
Yeah, so when we started out, first I ran on Amazon and the cloud, but I think I mentioned earlier, like most of the testing on our early demos were on commodity hardware, like 680s. Even I often demo on my laptop, which is just a 650M with 2 gigs of memory. So it runs on any hardware. You don't need K40s. K20s works fine. Anything with CUDA 3.0, I think, and above, or sorry, Compute 3 and over, I think, or 2 and over, I think it runs on. You asked about whether, like, about joins. I mean, it does do joins. It's basically you can do joins in several, like, you could possibly pre-partition on your join attribute, just like a distributed database. You're right, there are some limitations when you have less memory per card, and that needs to be explored by pushing some of it to the CPU, or, I mean, we can talk about this a bit later. But
MapD also runs on CPU, so you can have a large in-memory CPU system and it will run faster than other database systems. Any more questions?
All right. Well, luckily, both Tom and Todd are here in our booth. So if you do have any questions, you want to see more demos, or you want to do some fun correlations with all this amazing data that you have, just step right on over to the left and they'll be able to service you personally. Thank you again, Tom and Todd, and thank you, MapD.
thank you. Thanks so much.
Thank you very
Allison.
much.